In this video, we're going to be talking about two types of comparison tests, the direct comparison test and the limit comparison tests. So we have seen two types of series that are quick to identify when they're convergent and divergent, and those are the geometric series and the p-series. And so the idea of this section is that we can use those easy to identify series as a baseline for comparison for series that look similar but aren't quite of the right form, right? Series that maybe look similar to the geometric series and the p-series, but that aren't quite in the right form to take those tests. So the first we're going to look at is the direct comparison test. So very often just called the comparison test. I like the word direct to distinguish it from the limit comparison test. So the direct comparison test, or DCT. So suppose that we have two series here that have positive terms. So this test does not apply if the series terms are not positive. So two versions of this. If b sub n, the sum of b sub n, is a convergent series, and if every single a sub n term is less than the b sub n terms, then the sum of the a sub n is also convergent. Flipped around, if the b sub n is divergent, if the sum of the b sub n is divergent and the nth terms are in this relationship, the nth term of a is greater than or equal to, not less than or equal to, but greater than or equal to the nth term of the b series for all n, then the a sub n series, the sum of a sub n, is also divergent. And so what's going on here, the idea of this, if b sub n is convergent, and if every term is less than the b sub n, then you are less than, the sum of the a sub n is less than something that is finite. And less than finite is finite, right? If the b sub n are convergent, then their sum is finite, and less than finite is finite. The other way around, if the sum of the b sub n is divergent, well, because these are positive terms, if they are divergent, then they are going to infinity as you add them up. And if you have a sum whose terms are all bigger term for term than the divergent series, then the idea is that you've got something that is bigger than something that is infinite, and so itself is also infinite. That's the sort of the gist behind that. Is not a proof, but that is just the intuition behind this direct comparison test. So let's go ahead and look at this first example. So we've got the sum from n equals 1 to infinity of 5 to the n over 2 to the n minus 1. And we think, that looks like a geometric series. It looks like this, kind of, except there's something in the way. There's a minus 1. So it's close, but not quite. If only we could compare. Well, we can compare with a direct comparison test. We have to set up a little carefully. We have to check. We have to check that the conditions are satisfied, which means that we have to build one of these inequalities. We have to build one of these inequalities for comparison. So the first thing that we want to do is try and build this term in comparison to this term. So 0, we have positive terms, so 0 is less than 2 to the n minus 1 is less than 2 to the n. Yes? So if I subtract 1, I obviously have something less than. Now we are using a property of positive terms. If I take the reciprocal, right, if I have 0 is less than a is less than b, right, 0 is less than a is less than b, and I flip them over, well, 1 over b, right, 1 over b is then less than 1 over a. So this is a property of positive numbers, that if you take their reciprocal, the inequality flips direction. So this is what we've done here. 1 over 2 to the n is less than 1 over 2 to the n minus 1. Now, I can just multiply that inequality by a positive term, 5 to the n. So 5 to the n over 2 to the n is less than 5 to the n over 2 to the n minus 1. And do you see what I've done here? 5 to the n over 2 to the n is 5 over 2 to the n. That is our geometric series. And here is the term, the nth term of the series that we wanted to establish the convergence or divergence of. Since this series, the series here of the sum from n equals 1 to infinity of 5 over 2 to the n diverges. How come? Because it is a geometric series with r as 5 over 2, which is greater than 1. Since this series diverges, this series, which is term for term bigger than it, diverges also by the direct comparison test. Now, let's look at another example here, another example that compares to maybe not a geometric series, but to a p-series. So if we've got the sum from 1 to infinity of 1 over n squared plus 3, now this is making me think of the p-series, 1 over n squared. But again, it's not quite right. It's got a plus 3 in the way. If it's got a plus 3 in the way, what can I do? Well, let's try making a comparison. Certainly here, if I add 3 to n squared, then n squared plus 3 is greater than n squared using the reciprocal of positive terms, right? We are greater than 0. 1 over n squared plus 3 is less than 1 over n squared. This is the nth term of a convergent p-series. P is 2, which is greater than 1, so it is convergent. And so term for term, this series is less than a series which converges, and therefore it also converges by the direct comparison test. Now, a very common mistake is to say, since 1 over n squared converges, well, that's not what you mean. That is the nth term. That is not what we're looking at the convergence of. We're looking at the convergence of the series. That should be the series of 1 over n squared. Since that converges, this, again, that's not the convergence that you're trying to establish. You're trying to establish the convergence of the sum. So be very, very careful about this mistake. When you make your final statement, it is the convergence of the series that you are looking at and comparing. So one more example here of the direct comparison test. Let's say that we've got the series from n equals 2 to infinity of 1 over n plus 1. It looks like the harmonic series, and so I'm going to try and make a comparison again, but this, right, we have something in the way, the plus 1, and so we make the comparison here. N, if I add 1 to it, n is less than n plus 1. The reciprocal for positive terms, 1 over n plus 1 is less than 1 over n. This is a divergent p-series. The harmonic series is divergent. P-series with p equals 1. And since this term is, these terms are all positive, if they are diverging, if the series is diverging, then the series must be diverging off to infinity. And so this tells me that term for term, I'm less than something that is going to infinity. So my sum is less than infinity. Well, that tells me nothing. That tells me nothing, right? It could be an infinity as well. It could be, right? This is actually a little misleading. Telling you that it's less than infinity looks like it is convergent. That is not at all what I mean. What I mean is that it is less than or equal to, right? Less than or equal to infinity, right? It could be matching this term in terms of the infinity. So that tells us nothing. It is a case where the direct comparison test does not apply. Does not apply. And so what do we do? Well, you cannot use the direct comparison test. Luckily, there is also a limit comparison test. Also the limit comparison test here. So the limit comparison test, or LCT, goes like this. Suppose that the series a sub n and b sub n have positive terms again, positive terms. This time we are looking at not making a inequality comparison, but a fraction, a ratio comparison, a sub n over b sub n. If the limit as n goes to infinity of that fraction gives me c, right? And if that c is a finite number, so 0 is less than c is less than infinity, then both series either converge or diverge together. They behave the same way. So a couple of differences to point out with the direct comparison test. The direct comparison test used a inequality, not a fraction, and the direct comparison test did not use a limit. It was term by term. This is a limit. So there's a couple of differences here in the limit comparison test versus the direct comparison test. So let's look at the previous example, which did not work with the direct comparison test. If we imagine comparing this to the harmonic series again, right? We're comparing to the harmonic series, but we're doing the ratio of their terms, this over this, right? We're doing the ratio of the series terms, of the nth term of one series and the nth term of the other series. So if we do this, right, we've got a little bit of a algebraic manipulation to do here. So we do the multiply by the reciprocal. So we get this limit here, n over n plus 1 over n gives me 1 over 1 plus n. That term goes to 0, and so our limit is equal to 1. And since the harmonic series is divergent, right, it is a p-series with p equals 1, and since the limit of our fraction of nth terms became 1, which is a finite number between 0 and infinity, then this series diverges also by the limit comparison test. So the limit comparison test came in and saved the day, where the direct comparison did not apply. Another example here, and we have the series here, which looks just quite horrendous, quite complicated. So let's take a look at this series. We've got the sum from n equals, that should be 2, n equals 2 to infinity of the cube root of n squared plus 1 over n times the square root of n cubed minus 2n. And we have got a big mess there, a big mess. So we don't even know right offhand what to compare it to. So what we are going to do first is use the idea of an effective power to figure out even what we should compare it to. And the idea of an effective power is that the highest powers, when n is going to infinity, the highest powers dominate. So this term from the numerator, the cube root of n squared plus 1, well, as n is going to infinity, the plus 1 is almost irrelevant, and so this is approximately giving us the same thing as n squared, the cube root of n squared, which is n to the 2/3. Same thing here for the term in the numerator, the square root of n cubed minus 2n. As we go to infinity, the minus 2n is almost irrelevant, and so we've got something which is approximately, effectively, the same as the square root of n cubed, which is n to the 3/2 power. Therefore, our big fraction here, as we go to infinity, is effectively n to the 2/3 over n times n to the 3/2. You simplify those big powers, and you get 1 over n to the 11 over 6. And so that is telling you that your p series to which it would make sense to compare is the sum from n equals 1 to infinity of 1 over n to the 11 over 6. So if we do this limit comparison. So we're going to take one series term divided by the other series term and take the limit as n goes to infinity. If we do that, right, big, horrible looking mess, we can do some algebraic simplifications. Multiply up from the reciprocal here. We can factor out n squared out of the root, which leaves this. We can factor out n cubed from the root, which gives this. Right, combine all those powers of n, and what do you know? They give the same thing. Here's the side calculation, and they cancel, which leaves us with something quite delightful, because when we take the limit, that goes to 0, that goes to 0, so we end up with the limit is equal to 1. So since this is a convergent p-series, convergent because its power is 11 over 6, which is greater than 1, and since it is so important in your conclusion to state the conditions that you have checked and why they are showing you that you have a convergent or divergent series as a result. So this is convergent p-series. Why? Because it's this. And since this, right, this was the result of our limit, which was necessary for the limit comparison test, since we have c equals 1, which is between 0 and infinity, our original series converges by the limit comparison test. Let's look at one more example. And so what if we have this? The sum from n equals 1 to infinity of 2 to the n over 2 to the 2n minus 3. So what do we compare to? Well, a little bit of algebraic manipulation to figure that out. We have this sort of minus 3, which is in the way, but other than that, it makes us think of this kind of term, right? The dominant terms as n goes to infinity. If we do a little laws of exponents here, we get 2 to the 2 to the n in that denominator, which is 2 over 4 to the n, which is 1/2 to the n. So we will compare to a geometric series this time. So we are going to do, again, the limit of this term over this term, right? And so the limit as n goes to infinity of the nth term of one series over the nth term of the other. More algebra here. We have a reciprocal to bring up, so 2 to the n over 2 to the n, times 2 to the n over 2 to the n minus 3. Combine these two terms with the law of exponents, 2 to the 2n over 2 to the 2n minus 3. Factor out 2 to the 2n, right? Those terms are going to cancel, leaving you with this. That term quite conveniently goes to 0, so you get 1 again, and it might look like you'll always get 1. That's not true necessarily. When your series match very, very closely, it's quite common to get 1 as your limit value, but it is not the only value that is possible here in the limit comparison test. So since this is a convergent geometric series, why is it convergent? You must tell me r is 1/2, which is less than 1. And since, what was the result of your calculation? C equals 1, which needs to be between 0 and infinity for the limit comparison test. This series converges also by the limit comparison test.